Good morning, everyone. This is P. Venkata Mahesh, Assistant Professor in Department of Mechanical Engineering, Institute of Aeronautical Engineering. Today, we are going to discuss the first topic of the course on Computational Fluid Dynamics. The topic is introduction. We are going to give introduction on this topic. So, the outline of this lecture is like this: what is CFD? Why we have to use CFD? What is the history of CFD? And where is the CFD used till now? And we may see something about the governing equations derivation. Just we will see a brief review of the governing equation derivation. That also we will cover in this video. Now, what is CFD? You all might have heard CFD. CFD is heard very. Now these days it has become very famous. CFD. The full form is Computational Fluid Dynamics, but actually CFD is not just restricted to fluid dynamics. Okay, CFD is a broad area which covers not only fluid mechanics, heat transfer, mass transfer, and any other process which involve transport phenomena, transport of mass, transport of momentum, transport of energy, like that. Any other aspect can be covered in this using this CFD tool. Okay. Now, CFD is the integration of three branches. You can see here the engineering stream, engineering fundamentals, mathematical fundamentals, and the computer software. So the CFD is a separate branch, you can say, which is the integration of the engineering fundamentals, mathematics, and computer science. So with this, we can define the CFD in the following way. CFD is, or the computational fluid dynamics, is the analysis of systems involving fluid flow, heat transfer, and associated phenomena such as chemical reactions by means of computer-based simulation. So it is basically what we'll see is we'll do analysis and we'll get all the results in the form of a video. So that is the basic definition of CFD. Now, there are many equations, not many, few equations, but you can classify them as many. So, fundamental equations are there, and these fundamental equations are governed by some laws. Okay, the fundamental laws are governing some of these fundamental equations of CFD. Now, the first law is the conservation of mass. Law of conservation of mass means mass can be neither created nor destroyed. It can only transform from one form to another form. So that is the basics. From that we get this equation, and this equation is called continuity equation. And here you can see there is nothing related to mass. Okay, because the assumption for behind this equation is the mass, the density is constant. So the density is constant. Because of that, the rho is eliminated from this equation, and that is why this is the simplest form of continuity equation. So next law which is governing is the conservation of momentum. So the net force is equal to mass into acceleration. So what is this momentum equation based on? It is based on the Newton's law, which states that the net force is equal to mass into acceleration. So from that you can see here, this is the acceleration term and this is the pressure force, this is viscous force, and this is body force. So we have three forces which are generally these three forces are acting on the fluids that are flowing, and the net force is equal to the mass into acceleration. So this is the acceleration term. Now in this acceleration term also we have these three terms. These three terms are called the convective acceleration, and this is the local acceleration. So the two terms are there. One is convective acceleration and local acceleration. So that that is the sum of the acceleration. So this, the first four elements of these three equations, they represents the acceleration, and the remaining terms represent these three terms represent the pressure forces, and these three terms represent the viscous forces, and these three terms represent the body forces. So the next equation is the conservation of energy equation. So what is this? Is the energy, this is what is it, this is one, this is another another term, this is another term, this is another term. So these are energy can be energy can be transformed one form to another form. Okay, so that is the basis of this energy equation. It is the first law of thermodynamics. Based on the first law of thermodynamics, generally we derive this equation. We'll see these equations, derivation of these equations in the coming lectures. Just for the time being, these are the governing equations which govern the fluid flow, and we are going to analyze these equations. And now we'll see why we have to use CFD. Is there any other method with which we can solve these which we can derive the flow phenomena, or this is the only process or the only procedure with which we can find the flow phenomena? Now you can see here, this is a heat exchanger, and the heat exchanger, we have to analyze the flow through this heat exchanger. What happens to heat, what happens to the mass, what happens to the velocity, pressure, all those components, as well as the temperature aspects of this heat transfer, heat exchanger. Now if I want to fabricate this entire heat exchanger, it will take days. Okay, now sometimes if the problem is much complex, it may even take a month or two. So every time if I have to fabricate and analyze and see that the results are not good, and again I have to refabricate, it is going to take a lot of time. So this is the experimental analysis. Okay, so the experimental analysis, what we will do, we will fabricate the entire heat exchanger, we will analyze the flow through the heat exchanger, and we see the results, and if the results are not satisfactory, again we have to fabricate this, and again we have to do the analysis. So it is a very time taking process, and it is very costly affair also. The other one, simpler one, is analytical method. Analytical method means we can give the inlet conditions and we can find out the outlet conditions. So only simple things we can find out. But if I want to find the intricate details at each section, what should be the what is the temperature, and at each section what is the pressure, what is the velocity of the fluid. So if that is to be done, it will be very difficult and laborious task for this complicated system. So in order to avoid this complexity, the computational fluid dynamics is started being used. Okay, so they have started the computational fluid dynamics in order to get the advantage of the experimental fluid dynamics, and also take the simplicity of the analytical procedure. So this is the reason why we use the CFD. Now, as I said, the experimental procedure, theoretical procedure, numerical procedure, or CFD procedure, three procedures are there. Now, are there any advantages and disadvantages of these three procedures? That is what we have to see. Now, as I already said, in experimental method, either we have to develop the prototype or a scaled model. Model we have to make, or we have to make the prototype. Prototype means the actual object we have to make. Model means we will reduce the size or increase the size based on the based on the model. Say suppose I want to analyze this watch. Okay, watch, inside watch the gears and all very small, and if I want to analyze that, what I have to do, I have to increase the size, and the scaled model will be this bigger than the prototype. Say suppose if I want to analyze the flight, okay, the flight I cannot bring into my laboratory and do the analysis, experimental analysis. What I have to do, I have to make the scaled model or reduced size model of the flight, big flight, and which is suitable for the test section which I am having in the experimental laboratory, and then I have to do the analysis. So in either case, either I have to make the prototype or I have to make a scaled model. So the physical product is required, it is a must for experimental procedure. And then after doing the analysis, if I want to change the dimensions, they again I have to fabricate, and again I have to do the scaled model or prototype, again I have to do this. So it will take a long time, and because material is also involved, it is a costly procedure. Now, is it a absolute process? Are there no errors in this? No. In experimental procedure also there are errors, and it is also not an absolute one. There will be errors, and we have to minimize the errors. Say suppose the person is observing, so there will be some parallax error. And the scaled model if I am taking, so for making the scaled model, again we have to take some approximations, and that approximations also will lead to some errors. So in that way, experimental method also give the results, but there will be some errors which we have to reduce. Coming to theoretical method, it will give quick and exact solutions, but the condition is the geometry must be simple and the loading conditions should be idealized. If I have the realistic conditions where the temperatures are changing from time to time, the complex geometry, it is not a simple cylinder, it is the shape is if you see the aeroplane shape, it is not a simple one, it is a complex geometry. So in order to analyze the complex geometries, again this theoretical method is not possible. Now coming to the CFD, which is which comes under the numerical method, here what we are doing, we are replacing the complicated problem. Okay, previous slide we have seen a big heat exchanger. What we are doing, we are breaking down that heat exchanger into small parts. The process is called discretization. Now using that discretization process, what we are doing is we are breaking the complex problem into simpler problems so that we can apply our theoretical equations and get the results. So that is the advantage of this CFD. Okay. Now, are there any errors? Okay. Are there any errors in this CFD analysis? So CFD analysis errors we can reduce by the process called refinement. Okay. Say suppose a big object is there. This big object, if I divide into 5 parts, the error will be more. If I divide that big part into 100 items, the error will be less. If I divide this big object into million parts, the error will be very insignificant. So in that way, what we will do, we will refine the solution. Refine the solution by discretizing the object into very small parts so that the error is very negligible. So that is the way we use this CFD. Now, if I want to see the evolution of CFD history, when this CFD has started into the community, okay, when the people have started using CFD. Now, until 1910, okay, until 1910, people were developing the mathematical models and numerical methods. So there was only experimental analysis and people were working on mathematical models and numerical models based on the experimental analysis. Now in between 10 and 40, okay, these numerical models and methods, they have integrated, and they are using the hand calculations. There are no computers during that time, so only hand calculations they were using, and they were using these mathematical models which were derived up to 1910, and they are doing the calculations. Now in 1950s, the computers have come into the picture. With the advent of the computers, what people have done is they started applying these numerical methods into using these computers, and they started using a kind of CFD kind of things. Okay, now in 1970, okay, in 70s and 50s, between this time, what these people have started is they started some codes, okay, some commercial codes which are similar to the CFD codes that are available in the present day market, but it was restricted to academia. Okay, it was restricted to academia, only in research. It is not commercially available to everyone. Only in research domain they have developed their own codes, and they are not distributed outside. Now in 1953, the Kaugati, okay, what he did, he analyzed the flow around the cylinder. So that is the first time they used this computational techniques and analyzed the flow around the cylinder. And in 1967, the first paper was published using this CFD. Okay, the computational analysis, using the computational analysis, they have published the first paper. Till even then, the codes are not available for the commercial outside. Okay, and in 1970s and 80s, during that time, NASA started, so I mean they have invested so much of time and energy into this CFD codes, and the Boeing also, they invested a lot of time and energy into this codes. Because of their efforts, why they used these codes means they need high speed aircrafts. So the high speed aircrafts, the submarines, ships, they are all required for the fighting purposes. Okay, and high speed, because these high speed things generally they use only for the army issues only, not for the in this what do you say, the transportation purpose. So this initially they used these computational techniques for the submarines, automobiles, helicopters, aircrafts, all those things which are used for the army. Okay, then what has happened is the commercial codes after between 1980 and 1990, commercial codes have started coming. Okay, but they are not famous, they have just started, and the industry people, they are also started using these commercial codes. Okay, and in 2000 and 2003, the modeling software ICM CFD was introduced, and 2003 the CFX, the first commercial computational fluid dynamics software, was introduced in 2003. Then from there on, there are many commercial codes, which we'll see later how many commercial codes are there in the market these days. Now, where I have briefly described where the NASA, Boeing people have used this CFD. You can see here the aircraft, the shape of the aircraft. In order to make it high speed, the shape should be modified. So these Boeing people, NASA people used this CFD, and they optimized the shape of the aeroplane. So if they have to do this experimentally, it will be very costly here. Again, I am saying reiterating the same thing. The making of this entire aircraft and testing and analyzing and again redoing it, it will be very costly affair. But with these CFD techniques, this has become very in hours we can get a different shape. Okay, based on the computational facility. If you have a supercomputer, you can get it in hours. If you have a small computer, you can get it in days, like that. Now this is the engine, aircraft engine. Inside aircraft engine, how the flow is happening. Here these blades are there, so leaving the blades, how the flow is happening, and inside this combustion chamber, how the flow is happening. All these things we can clearly analyze using this CFD. And the aircraft, I mean this is a helicopter here, how the fluid, that is fluid flow is happening around the blades, helicopter blades, that also you can see here. Now they started using with this aerospace purpose, but what happened, this CFD, it has stretched its application to different areas. So this you can see here, this is the computer cabin. In computer cabin, how it should be designed so that this air flow through the computer cabin is proper, so that it will not have heating issues. So initially this computer cabin was very huge. Nowadays the computer cabin, CPU cabin is very small. So that is possible because of this CFD analysis. And this is the refrigerator. This is washing machine. Now you can see here, this is a commode. This is the commode of your toilet. And here also people have started using CFD to analyze the fluid flow and optimize these parts. So the CFD has come from air helicopters or aeroplanes, from aerospace application to our toilet. Everywhere CFD is being applied. Now if you see in automobile sector, here automobiles also, this is a race car. For race car, the speed should be high. Speed should be high means the drag resistance also should be low. So in order to analyze that, again we'll use CFD. This is the engine, how the fluid goes inside, how it combustion happens, and what comes out. All these things, they are using the CFD. Now the cabinet, the car automobile cabinet, it for comfort of this passenger, how it should be for the comfort of the passenger. For that also CFD is used. And this is the cooling system, you can see here. And in the cooling system also, how the entire cooling system should be there, so that the engine will not get heated up. So this is another very important area where the CFD is used. Next one is the biomedical. Even in biomedics also, people started using CFD. And here it is called microfluidics. It is called microfluidics. Microfluidics, why we are calling this microfluidics? The arteries, any blood vessels and air vessels that are inside our body. These are vessels that carry air inside and outside of the lungs. Okay, and these are arteries that carry the blood. So how the blood flow is happening, how the air flow is happening. And because of the analysis of these kind of things, people have started using artificial lungs, artificial hearts, all those things people have started using. Now in chemical industry, if you see, this is a gas sprayed stirring tank. Okay, this stirrer is there, and the gas is coming out of this stirrer, and the stirring is happening. And how this entire process happens. So here in this, it is showing the vectors of this flow, how it is happening. And here the fluid flow simulation is shown here. How this happens in a container, that you can see here. So chemical industry also, people started using CFD. Now in civil engineering, you can see here civil engineering, this is a dam, and how the flow happens through the dam, so that the spillways and all those things can be designed optimally. So the people are going for optimization of the material and cost. So in order to get that optimal solution for the spillways of the dams, they are using a CFD. Now here you can see the tall building is there. So this big building, as the height of the building goes high, what happens is the wind speeds are very high. Okay, the higher atmosphere, the wind speeds are very high. At that high speeds of the winds, what happens to the building? What kind of drag resistances, what kind of loads will be applied on the building because of this high speeds? That also people started analyzing. Not only outside, inside also they want to optimize the space. So in order to optimize the space, how the airflow happens inside the compartment, inside the room, inside the compartment, inside the building, any place, all these areas people have started using CFD. Now you can see the refrigeration and air conditioning. So this is the heat exchanger. Initially we have seen the, here you can see the analysis, a computational analysis of that heat exchanger. And now this is a centralized, we people use so many centralized air conditioning in movie theaters and big halls. We can see this kind of ducts, and these ducts are huge in structure and they are very complicated in shape, and analysis of that is not easy using mechanical or analytical procedures. So we have to use our CFD techniques and do the analysis. And this is the compressor which is used in the air conditioning or the refrigerators, and this also people are using. So in this R&AC, refrigeration and air conditioning area, people used. So this is the ship. Under the ship there is a propeller, and the analysis of this propeller, the shape of this blade should be optimized. For that also CFD used. And this boat, the shape of the boat, below this boat, the shape should be proper optimized, for that having the minimum drag resistance. And here this these boats are run by the wind. Okay, now we have to take more advantage of the wind, and the drag resistance should be less. So in order to have that advantage, what we have to do, we have to use the CFD. So in oil and gas industry means we have to, when extracting the petroleum, this will go inside the earth. How the slurry will come out, that also people are using CFD. And the offshore, the oil, generally this oil pumps which people extract the oil is inside the sea, and the structures are very tall, and the wind speed on the seas are very high than the on the shore, on the land. So in order to have the optimal construction, what we have to do, we have to analyze the drag resistance, how much it happens because of this high speed winds on the offshore conditions. So that also people are using CFD. And even inside this structure, we have the places where the fluid is coming out, and while construction the slurry is coming out, and the fluid has to go to some from this place to another place. All these areas, how the fluid flow happens, how the petrol flow happens, that people use to CFD for analyzing that. Coming to the power sector is not left behind. Power sector also people are started using CFD. So this is the hydraulic turbine, how the shape of the blade, or the blade shape and the angles, all those things should be optimized so that we get the maximum power of the water. And this is the gas turbine. Not only here you see the blades, okay, and the air has to flow inside through these blades, and the combustion chamber will be there, and how the combustion happens, all the entire thing is being simulated in CFD. And finally the optimized geometry is given to the person to fabricate. Okay, and this is the steam turbine. In steam turbine also, how the steam flow happens, and what should be the optimum shape. Well, these days, previously they used a smooth surface here. Now they are optimizing that with something called end contouring. Okay, end wall contouring. Using that, they are optimizing the shape so that the these losses are less. And this is the wind turbine. So wind turbine, it is a huge structure. Again, in order to analyze that, we use a CFD. So like this, in power area also CFD is being used. Even in sports, you can see the application of the CFD. See, yes, person swimming, how he has to place the hand. If he place the hand like this inside the water, what will be the resistance, drag resistance, and in which direction he should place the hand inside the swimming. And this is uh, the helmet for the swimmers. How, these days people are using helmet also for swimming, so that the uh, resistance is small. And even these helmets are used in this bicycling. So here also people are using CFD for analyzing. The purpose of CFD is optimizing the shape to get the minimum resistance and maximum output. So this ball is there, and what should be the optimum dips, all these dips on the ball, and where what should be the placement of these dips, all those things where they are using CFD and analyzing. And even in metallurgy thing also, this is the blast furnace, how the combustion in the metallurgy blast furnace happens, how the exhaust, the gases flow outside, all those things people have started using CFD. So these are the broad areas where CFD is used. Now what we will see is the governing equations. Okay, so still now what we have seen what is CFD, why we have to CFD, and where CFD is used. While discussing why we have to use CFD, we have seen some equations, some governing equations, and for what we will do, we will derive one by one. Today we will just see the first equation, the simplest one, continuity equation, and the continuity equation, how to derive, that we will see. So we have two procedures. One is this integral procedure, and the other one is the differential procedure. Both we will see, and the final answer will be same. Now the basis of this continuity equation is mass conservation. Mass can neither be created nor destroyed. It can be changed from one form to another form. So the mass is conserved. Okay. So if I take any, say suppose this room is there. Okay. If the room is closed, the mass is constant. If I open this, some air can come inside, some air can go outside. Then what happens to the mass? So all those things that we have to see. Now what we are doing in this derivation is we are taking the fixed volume. Okay, so this is the fixed volume, and we'll see what is the mass flux crossing the boundary, how much mass is going, how much mass is coming, and what is happening to the mass. Now this is the integral form. This is the volume derivative, and this is the surface derivative. So differentiation with respect to time of this mass. Okay, so this rho is density and dV is volume of the that small box we have taken in the previous slide. Okay, this is having some volume, and if I multiply with the rho density, I will get the mass, and change in mass with respect to time. This is the volumetric volume integral, and this is the surface integral. Surface integral, what it gives is how much fluid is going inside and how much fluid is going from the surface and coming inside the surface. The change in mass with respect to time is nothing but the net heat flux through the surface and inside the surface. So that is these are the two things. If I apply the Gauss divergence theorem, this surface integral can be transformed to the volumetric integral. Okay, so this surface is integral is transferred into the volumetric integral. Why we are doing is, we can now, instead of this surface integral, you can use the volumetric integral and we keep in that equation. So this is the final equation. Now both sides we have volumetric integral, we can take this one to that side, and here it should be minus, so that it will come that side, and it will become plus, and it is dou rho by dou t plus delta del dot rho v. Okay, now this entire integral is equal to 0. Now integral of something is equal to 0, so in the internal component we are taking, that we are making it 0. Now here if I put that one here and this del, if I expand into Cartesian coordinates, what I will get is dou rho u by dou x plus dou rho v by dou y plus dou w by dou z. So this is the continuity equation. This is the one way of approach, and here everything you have to remember. Okay, in these two slides what we have seen, everything you have to remember. Now there is another approach which is easier, and generally in graduation level people will do. That is, they will take a infinitely small volume like this, and they will see how much mass is entering, how much mass is leaving in all the three directions: x direction, y direction, z direction. So the amount of mass entering, amount of mass leaving, the net mass, the difference is the net mass. The net mass entering in x direction plus the net mass in entering in the y direction, the net mass entering the z direction. The sum must be equal to the rate of change of mass of that element. So that is what we have to equate to get the continuity equation. Now here u is the velocity, and delta y delta z is the area of the surface perpendicular to x direction. Okay, so suppose this is the, if I am seeing from here, and this is delta y delta z. So the product is our area. So the area into the velocity, if I multiply, I will get the volume flow rate, or you can say it as a Q. Now volume flow rate into density, if I multiply, I will get mass flow rate. Okay, density into volume flow rate will get mass flow rate. Now that is what we are using here. So this is rho into u into area, that is the mass entering in x direction. Now this is the mass leaving in x direction. Now is the velocity constant? No, the velocity is changing in x direction. At what rate it is changing? So the change in velocity, what is this term? This term is the change in velocity in x direction. Okay, so the change per unit length, it is giving the change in velocity in x direction per unit length. Now what is the total length? Total length is delta x. So change in length, change in this mass flow rate, change in mass flow rate with respect to x means change in mass flow rate for unit length. If I know that and I know the total length, I can find out what is the total change in the mass flow rate. So this term is total change in mass flow rate in x direction, and this is the initial mass flow rate. So if I add these two, what is the mass flow rate at the exit I will get? So this is the inlet mass flow rate. The exit mass flow rate is equal to the mass flow rate at the inlet plus the net change in the mass flow rate in x direction. So that is this term. So if I if I add these two, this is the total mass flow rate in x direction, and multiply with this area. So this the area is common, area is not changing, so same area we are using. So this is the net mass flow rate entering and this is the net mass flow rate leaving in x direction. Similarly, I can write for y direction and z direction. So the mass flow rate of change of mass is equal to the difference of mass entering and leaving, that we have to add. So x direction we have seen the mass leaving the space in x direction. Okay, this is the net mass leaving the surface in x direction. Similarly, the net mass leaving the y direction, the net mass leaving the z direction is given like this. What we have to do is the rate of change of mass of the element is equal to mass entering, net mass entering in x direction minus net mass leaving in the x direction, net mass entering in y direction minus net mass leaving in the y direction, net mass entering in the z direction and net mass leaving in the z direction. So this is if I equate these two, what will happen is this delta x, delta y, delta z, it is a constant on both sides. So I can eliminate that delta x, delta y, delta z. Another thing, here rho u delta y delta z is there and here minus rho u delta y delta z is there. So this term is eliminated and this term is eliminated and this term is eliminated. If I eliminate all these terms, I will remain with these terms. This is the final continuity equation in Cartesian coordinates and it is the conservation form. Okay, if anyone asks what is the conservation form of continuity equation, this is the conservation form of continuity equation. We can apply some simplifications saying that it is a two-dimensional flow. Two-dimensional flow in the sense, say suppose the length is very, this much is length is there, but the height is only this much. This is very insignificant when compared to this length. So what happens? The flow is influenced by this thickness, but in this y direction, I mean z direction, say suppose this is z direction, this is y direction and x direction. So this z direction, because the length is too large, the effect is very less. So that is what is saying here, the flow remains invariant, okay, in that z direction. So what happens is we can take only two directions and that is the reason the continuity equation is simplified to two terms for a two-dimensional flow. So if anyone says what is a two-dimensional flow, what is that means? One direction, the flow characteristics are not changed. Okay, they are not going to change in one direction, then it is the two-dimensional flow. Now in this also, if the density is constant, rho is constant, then this is the equation. So this is about the continuity equation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.